Gabor functions. Now, as I said, you can form a wavelet basis. The wavelet basis is given by a translated and scaled version of some basic mother wavelet. H is the mother wavelet. X prime, Y prime, lambda 1, lambda 2 are some parameters. The factors lambda 1, lambda 2 can stretch or expand or shrink the function, and x1, x2, xy, y prime are the shift parameters. You can also put a rotation. If you want to call it as a wavelet transform, then you can compute these coefficients for the parameters just by taking the projection of fxy with each of these wavelet functions with a normalization factor. So you have contraction, dilation, translation of the basic mother wavelet, and rotation if necessary. So in the formation of a Gabor filter bank, we need to make some small modifications. William Ralston did his master's thesis on this topic with me. The real component of the Gabor filter acts as a matched filter to detect broad directional components, assuming that the components are brighter than the background, the cosine function. Otherwise, you use sine, or you reverse the image. The parameter sigma specifies the spatial extent of the filter. Lambda specifies the aspect ratio of the filter that modulates the sigma value. If lambda equal to 1 and the phi parameter is not specified, then it is isotropic. So it can turn into just a simple bandpass filter. In the frequency domain, this results in an oriented filter occupying the middle subsection of the corresponding ideal fan filter. It is a fan filter, but it is taking a part of that fan filter as a bandpass filter depending on the scale and the orientation given by tan inverse V over U. So these specify the Gabor filter bank. Now, how many of these you need depends on the resolution of the details you want to capture, the size of the objects you want to capture. So you don't go minus infinity to infinity. That's just a theoretical convenience in representation. So there are some parameters that we used. For this test image, we used only those 4 angles. So you may convolve the band-limited and decimated versions of the image with the same analyzing wavelet. When you do multi-scale analysis, there are 2 possibilities. You keep the image fixed and change the wavelet scale. Or you keep the same wavelet and downsample and shrink the image, change the scale of the image. So 2 possibilities exist. But if you are given a small finite-sized image, then you can only shrink it so many times. After that, you lose all details. So one needs to be careful in the application of scaling to the given image. Now, when you have a Gabor filter bank, you could take the output of each one of them, or you may combine them using some vectorial addition of the components. Vector in the sense, the output of each Gabor filter is an image with some pixel values. But there is an angle associated with that image because an angular filter was used. So you take the angle of the filter that gave that output as the phase or angle, and the pixel value in the output as the magnitude, and then it's a vector. So each pixel can be treated as a vector in the output image, and at every pixel you can compute a vectorial sum of the components you have obtained. So decimation and filtering at each scale will provide you these images, and you may need some interpolation of the decimated and convolved images because you have downsampled them. You have to go back to the original size, and then they can be added to obtain the overall response, added either directly or using the vectorial format. The vectorial format is this. Suppose you have 4 components for the synthetic image, we only had 4 components. So 0, you get that response for the horizontal filter, 45 degrees to get that for 1 pixel, 90 degrees and 135 degrees. Do a vector addition, that is, copy these vectors and add them all up, and you get that as the output. So this is the vector addition. You're copying this vector here, that here, and this here, complete the polygon. So the output at that pixel has this angle, some, let's say 40 degrees or so, and that magnitude. This is advantageous when you want to do directional analysis of an image with components at various angles, and you're using only a few filters at a few different angles. In this image, we only have components at 0, 45, 90, 135. But suppose your image has components at all angles, but you don't want to use 180 filters, 1 for each degree. So you may say, I will use 6 filters, equally spaced 0 to 180. But the angles could be in between the filters' angles. So then you do vector addition, and you get the actual angle by interpolation of these output values. So here we have the same test image, Gabor filtering at 0 degree or horizontal with 1 to 1, 2 to 1, and 4 to 1 decimation. When you decimate 4 to 1, you see the thick bands are obtained. When you have 2 to 1 decimation, or even the original 1 to 1, the thin bands, these thin lines are detected. But they are not detected here, in the sense the response is low. So when you do decimation of the image, then you are taking into account the variation in the size or scale or thickness of the objects. Some get detected at some scale, some others get detected at other scales or give a high response. When you add them all up, you get this output. Now, none of these is perfect, of course. It depends on the nature of the image, the quality of the image. Decimation in the image causes loss of resolution, loss of clarity, and could cause other artifacts. So this is a sort of a mathematical possibility and notation, but in practice you may rather change the scale of the wavelet. That may be better than downsampling of the image or decimation. We did multi-scale edge detection using zero crossings that I showed earlier. My postdoc fellow, Yixiang Liu, he did this work with the log filters, Laplace-Gaussian Gaussian filters, and got zero crossings and got that map. I won't go through this detail. If you want, you can read this later on. It includes a number of very specific conditions for that kind of image to find the two sides of a potential rectangular pattern or line pattern, and getting the width and so on. So I will skip all of this, how to find opposing edges of a given line pattern, and I'll just go to the next section. There are some images I'll show later. Now we saw that the Hough transform can be used to detect lines. The Radon transform that is used in computed tomography involves projecting an image at various angles. So there is an angular dependency of the projection and what you compute there. So the Radon transform contains some information about angular distribution if you were to take the Radon integral at multiple angles, which is done in CT and MR reconstruction. There are some similarities between the Hough and Radon transform that you could use to advantage and combine them and come up with a combined Hough-Radon transform. My master's student, William Ralston, came up with this transformation and came up with this implementation of the two transforms together. We have done some other work also for the detection of the pectoral muscle and the nipple using such transformations later. But Ralston wrote this paper on combining the Hough transform with the Radon transform. The Hough transform is primarily applicable to binary images in the sense you must first detect the pattern and you are required to have a binary image where every pixel contributes to the output, to the transform, Hough transform domain. So there is a detection step required first, edge detection or line detection or something. I did mention in the detection of the pectoral muscle that the incrementing of the accumulator need not always be by 1. It could be incremented by the intensity of the output in the detection process. So it is possible for the input to have some grayscale variation, but you don't put the original image directly. That doesn't help with the Hough transform. With the Radon transform, you take the original image and integrate at various angles using straight lines passing through the image at multiple intercepts or displacements for the same angle for parallel beam projection. In this book, there is a separate chapter on image reconstruction from projections where I have described the Radon transform and reconstruction from projections. So the results of the Hough transform are dependent upon the binarization method or the detection method to segment the image and get the patterns. So we said we use rho equal to x cos theta plus y sin theta as the equation of the line. Any straight line is bounded in angular orientation by 0 to pi and bounded by the Euclidean distance to the farthest point on the image from the center, assuming the center of the image is the origin. So we saw that for a given point xi, yi in the image, we obtain a sinusoidal curve in the Hough domain rho theta. So rho naught equal to xi cos theta naught plus yi theta naught. So each point xi, yi lying on a straight line with rho equal to rho naught and x equal to x naught in the image domain corresponds to this sinusoidal curve in the Hough domain. For each point in the image domain, the Hough transform performs a one-to-many mapping, resulting in a modulated sum of sinusoids. So all of these sinusoids are added up for pixels along a straight line. It is a kind of an accumulation procedure, also called as a voting procedure. Each pixel contributes a vote. Am I on a line or not? What are the coordinates of my line, of the line on which I exist? So in the Hough domain, we do peak detection. We saw that. If you look at the Hough transform, that line is indicated by the theta angle of the normal to the line and the distance along the normal from the origin to that line. In the Radon transform, the same line is defined. The origin is taken to be in the middle of the image. It doesn't matter, some origin. And then you integrate the image along that ray. You call it as a ray, like an X-ray. X-ray photons are going along that ray and they get attenuated as they pass through the medium. And then you get one ray integral. You displace and then get that kind of an integral for all rays at that angle. If you use some of the scanning geometry, you can rebin the measurements to parallel ray geometry if you wish, or do reconstruction directly. There's a problem with the Hough transform with crosstalk. I mentioned that if a line is of 1 pixel thickness, it gives you all those sinusoids, they intersect at one point. But if a line is thick like this, it's a rectangle. There are many pixels in this rectangle, but you can form many lines by connecting many pixels. So there could be lines of various angles within that thick object, which is not a line, but assume this is a line. Then I can draw so many lines connecting various pixels. I can even draw a line this way. So this thick rectangular line contains lines at various angles if you go one pixel at a time, and that's what we could call crosstalk between multiple straight lines in the Hough domain. If the image contains several lines parallel to the x-axis, they correspond to several peak lines in the Hough domain at different values of rho for theta equal to 90. But then points in the direction perpendicular to that at theta equal to 0, you have a number of lines. I can take this point and this and connect, and that is perpendicular to those lines. So I get false lines at other angles. So this is an illustration of crosstalk. I have a number of lines that are horizontal in this case, but I can take pixels there and join them. These lines are broken, but still, the Hough transform counts this, all of them together and gives you a line. Says there is a line with so many pixels in this direction, which is orthogonal to those lines. And you detect all of these lines for all of those pixels. And if you have a thick line, as I said, I can draw so many lines within that at various angles. So you get a spread. So you combine the Hough and Radon transforms. The Hough transform may be viewed as a special case of the Radon transform, but the origin could be shifted. Now you could define the Hough transform with the origin in the center of the image also. You just shift your equations. In programming, previously in Fortran, you were not allowed negative indices, you were not allowed zero index value. Some languages like Pascal started allowing, I could say, minus 50 to 50, including zero. And then came other languages, some of them allow negative, some don't. MATLAB doesn't allow zero. MATLAB, you have to go from 1. So we are back to Fortran type of indexing with MATLAB. When we were writing programs in Fortran, it was being criticized, well, I can't handle the origin as 0. Or I want my time to run from minus 50 to plus 50. That was cited as some big drawback, but now MATLAB is big and we have the same problem. Pascal allowed that, and C, I don't know, doesn't allow. Does C allow negative index? No. 0? 0 is yes. Okay. So MATLAB doesn't allow those. So that's one of the problems, but it doesn't matter. In your computation, you just adjust the equation. So shifting the origin is not a big deal. So in the method that Ralston developed with me, the Hough-Radon hybrid transform is computed by updating rho I theta I by adding the pixel intensity and not by incrementing 1 as in the Hough transform. That's about the change. There is no big difference. We already did that in the detection of the pectoral muscle. We did in the sense I described that, but this work by Ralston was done a few years before the other work. So a line here gives you a bunch of sinusoids like you have seen before. And the incrementing is done by the intensity. In directional analysis, it is of interest to obtain the number of pixels or the percentage of the image area covered by linear segments in a particular angle band. That is what we want. So we need to form another parameter space with the number of pixels. Here the intensities have been added up, but you don't know how many number of pixels are there. So you need to have another space, like the Hough space. The shadow parameter space is the Hough transform of the image with no threshold. So you need to have another measurement. So here we have an image with 5 segments, and we have the Hough-Radon space. There are these points where these curves are intersecting, but note that these are thick line segments, so these areas of regions of intersection are not single points. spread over. Now, which peak do you detect? Of course, you can say in that region I want to find one peak and take that one parameter. But if you just compute the angular distribution, we get this, which is not very good. There are only 5 angular components, but I'm getting such a big spread. So this method has its limitations. We filtered the Hough space to detect these regions and eliminate others so that the search in the Hough space, Hough radon space, could be made a little better. So we call these butterfly patterns, and we could search for that. So filtering and integrating in the Hough radon space. So there are some methods given in the literature, 3x3 filter to locate the maxima in the Hough space and connect collinearities, that is pixels that are along the same line, in an edge image space. In our work, this concept of a butterfly was used, and you could manipulate the pixel values of filter using this concept. The filter used is this, which is a kind of a derivative in one direction and smoothing in the other direction. Let me see if I can. With the more complex images, things get more messy. This is a collagen fiber electron microscopy image. We can see fibers, but they are not clearly separated. So practical images pose more problems than what we can imagine and simulate in synthetic images. So the Hough radon space is this, very complex to detect peaks. What are local peaks here? So the lines are thick and there is some other substance in between. The lines are not clearly defined. You could take a derivative of this and so on, but perhaps Gabor filters will help, as we'll see later on with mammograms. So this is the filtered Hough radon space, and hopefully that will help in detecting peaks, local peaks. And if you were to use that information and make your measurements of the line thickness, then we get this rose diagram. It shows a large component here at this angle, a little less than 90 degrees, so that is okay. There is some dispersion here, but all of these are false. Are there horizontal fibers here? Maybe a little piece, but I can connect all of these and draw horizontal lines that are not in the image, but the algorithm will connect these high intensity pixels and cause the artifacts telling, well, there is a horizontal line there. So these are some limitations of the methods. All methods have limitations. You can formulate additional filters and techniques to reduce these, but this hasn't worked well.
So the angles, we are setting the angles. In this method, are we setting the angles or are they being automated automatically?
Which one?
In this one,
Yeah.
it is going under different angles, right?
Yeah.
But are they being setting, we are setting it or it's being detected automatically?
Well, the angles are measured automatically from the Hough radon space. The angles are obtained, one of the axes of the Hough domain is angle, and the other is number of pixels or added intensity.
Yeah, but then Gabor filter, we are setting up the angles, right? Like, so,
Gabor filter, you get the image itself. You get a filtered image. I'll show you that.
yeah, but we are setting up the angles over there, right? In the Gabor
We set the angle, correct.
filter. Here we are not setting.
No, here we're not setting, well, setting in the sense, it is implied in the Hough space. The coordinate along one of the axes is angle. The other is number of pixels or intensity. So yes, we are setting, but we are allowing it to span the full range, 0 to 180. And Gabor filters, I have to specify the angle for each filter, and I have to apply the filter and get the output. Here, all angles. But you can specify, you can say that I want it only from minus 70 degrees to plus 70 degrees. If you know that your patterns of interest are in that range only as we did for the pectoral muscle. We didn't go 0 to 180.
So it can be either angle, right? Either X.
No, one axis is angle, the other is the number of pixel counts or intensity. Whether it is this way or that way, it's your formulation.
Angular bands can be specified, like suppose here 0 to 91 to 5 series.
Oh, the Rose diagram, there we bin it.
Bin.
Okay. The Rose diagram is obtained by binning, by including all components in that angle sector. I don't know how many do we have here. 1, 2, 3, 4, 5, 6. So 15 degree bands. So we don't plot the output for every degree. It'll be very noisy. So 0 to 15, they're all put in that one band. The same for other Rose diagrams I've shown you. You can specify 10 or 18 or how many ever band bins you want for the histogram. Histograms always have bins. In the case of gray level, you only go one level at a time, 0, 1, 2, 3, and so on. Here, if you go 0 degree, 1 degree, and so on, you may not get many pixels. And also, you may not have that resolution in your computation. So you use larger bins of 15 degrees each. Okay? These results are far from perfect. So let's look at a few applications now. These are all the methods. In my book, the first few sections are methods, and towards the end, I have biomedical applications. Sometimes those sections also have some equations and methodology. So I've already said ligaments are highly organized connective tissues that hold bones together across a joint and hold the joint together. They consist of nearly parallel arrangements of collagen fibers that are attached to bone on both sides of a joint. Now, nearly parallel, but there is a wavy nature to that, like the strands of a rope. A rope doesn't have all strands straight. It is twisted. They are intertwined. But if you take a small section, the strands of a rope or a rope, whichever material it is made of, will have straight lines. So injuries to ligaments are common due to sport. In Canada it is ice hockey, it could be soccer or football. Cricket also, they run. If you fall and twist, then the ligament could be ruptured, and unfortunately they don't heal. They don't heal well because the ligaments normally don't have blood supply going inside the ligaments, because if you have blood supply inside and there are vessels with liquid, then the ligament doesn't have the strength. So when there is injury and ligament is ruptured, or it is, in this case, in our studies, they were ruptured surgically in rabbits, the healing process starts. And the healing process is facilitated by more blood supply. New blood vessels develop and collagen is deposited. New collagen material forms in the injured area and scar tissue develops. And scar tissue will not have the same organization of collagen fibers as in the normal case. Slowly over time, over a month or two, the organization changes from disorganized random distribution to an organized distribution that tends towards the original distribution, but not always, not perfectly. And also the blood vessels that came in, that were developed to facilitate the recovery process or the healing process, they go away after that healing process is complete, and the number of blood vessels and their thickness will reduce so that the ligament can bear load. That is inside the ligament. But epiligament, that is just outside the surface of the ligament, will have more blood supply, more blood vessels than the core of the ligament. So the injured or healing ligament or injured or healing joint may become loose or unstable because of lack of support through these ligaments because they are torn or they are still healing. This was done in collaboration with Dr. Frank, who was a famous orthopedic surgeon, and his colleagues in Calgary, and Dr. Subhashish Chaudhary, as I mentioned, the previous director of IIT Mumbai. He was my MSc student at that time in the 1980s. So a critical factor at that time in studies through observations that was thought was that blood supply is important in healing, and the organization changes. And the reorganization or remodeling of collagen fibers is important in gaining strength back in the ligament. Okay, I think I said all of that. The process used, if you refer to the first chapter, if you go through the section on electron microscopy, the ligament itself is taken out of the rabbit and it is frozen and fractured. The 3D ligament, it's very thin, of course, it's maybe a couple of millimeters thick and a few millimeters long, frozen and fractured. So the fractured surface shows the collagen fibers. There is some process of coating with various material, and then it is scanned using electron microscopy. The surface is scanned, so we get a picture like I showed earlier with the collagen fibers. So we did directional analysis using sector filtering, using that weighted fan filter with the cosine function and the Butterworth and linear filters. We obtained directional components over 12 angle bands spanning the range of 0 to 180. So each angle band is 15 degrees wide. So here is an image where you can see some of these oriented components clearly. And the binarized and directional components for the angle 75 to 90 degrees. So that comes here. You don't see the other components here. These come in the 0 to 15 degree band. So these were thresholded. We used Otsu's method and a few other methods to find the optimal threshold. So these are thresholded binary images. You count the number of pixels, multiply it by the pixel resolution, but that's a constant scale factor, and get the angular distribution. So you can see that most of the fibers are running close to vertical. This is 90, 75 to 90, 60 to 75 degrees. The other angle bands have very little in them. So this agrees well with that image. In the case of scar tissue, this is for 75 to 90 degrees, 0 to 15 degrees. It's a little hard to see orientation here visually. But a computer algorithm will say, oh, okay, well, look at that. That is horizontal. Look at this, it is horizontal. And so on. There is a piece there. So within that, you get whatever is horizontal. And now it has a broad distribution, nearly uniform. So this is scar tissue. We were given a number of these images. In those days, the electron microscope pictures were taken on film and printed on paper, and then we had to scan them using a TV camera. It was a TV camera which had 380 by 440 pixels or so. Very poor resolution, but that was the state of the art then. There was a big cable going from there to the computer in the AC cool room, and that introduced a lot of noise, which is what you saw in that clock image. If you remember that clock image, that was a clock in our lab. We took that picture with that TV camera and the digitization frame buffer in the computer room. With the cable having so many BNC connectors and other connectors, there was a lot of noise. So that was a real noisy image showing how much noise was introduced in this process. And the resolution is poor, and these are prints of scanning electron microscopy images. So there were a number of images. Unfortunately, many rabbits have to be sacrificed in this case. And by the way, the Foothills Hospital and most hospitals, perhaps here too, they have an annual event or an event quite often where there is a kind of a ceremony to thank all the animals that gave up their lives. They do that in Canada too. So there is a process to acknowledge that some lives were taken of lab animals to create data of this kind. Unfortunately, destructive. So the procedure was, the rabbit was taken and its ligament was ruptured surgically, and then it was allowed to heal. And the question is, what is the healing process? Do you want the joint to be immobilized in a cast? And for how long? Like if you break a bone, then you put a cast. But for how long? How many weeks? Too many weeks, then your muscle will atrophy and you will have problems in regaining strength. Too soon, the bone will not have healed and will not have the strength. And there may be other methods of facilitating recovery. Which method is the best? So how do you characterize that and determine objectively what should be these parameters for treatment? So that was the question here. So after injury inflicted surgically, the rabbits were allowed to heal, one by immobilization of the joint, like a cast, and the other, they were let free in the sense they could use that joint without any restriction. And here we have images of individual single samples. 3 weeks after injury, that is 3 weeks of recovery, 6 weeks and 14 weeks, without immobilization of the joint after injury. And here, 3 weeks, 6 weeks, 14 weeks with immobilization of the affected joint for 3 weeks. So you see that if you do not immobilize, at 6 weeks there is not much organization. 3 weeks there isn't much organization at all. The joint has been free after injury. 6 weeks there is some recovery, 14 weeks there is some more orientation. But these are different rabbits, different ligaments. One sample, once you take this out from the rabbit, that rabbit has to be sacrificed. So here there was immobilization for 3 weeks, and at 3 weeks there is already good alignment at a slightly different angle, that doesn't matter. And 6 weeks and 14 weeks. 6 weeks there is very clear alignment. So this is the collagen remodeling process in individual images, one image of one ligament of different rabbits. For each ligament, many images were taken, and there were a few rabbits involved in each of these. So these are the composite rows diagrams of a number of images and a few rabbits. I don't, those numbers are there somewhere. So on the left-hand side, without immobilization. This is with immobilization for 3 weeks. So if you don't immobilize the joint at 3 weeks and 6 weeks, there is still full random distribution. At 14 weeks, it looks good. If you immobilize for 3 weeks, there is good alignment already, that gets better and better. At 14 weeks, both of these are same, which means after 14 weeks, the ligament is healed regardless of your treatment process. In terms of this, whether the rabbits were happy or not, that's a different question. But the alignment looks good. But you reach this faster if you immobilize for 3 weeks. So that's the conclusion. This is objective analysis of the recovery process and comparing two different methods of treatment. And we did 3: immobilization for 6 weeks also. So 3 weeks immobilization, you are there, and let me make sure. Here. This one is 3 weeks immobilization. From there, at 6 weeks you are here, and then you are the same, meaning the entropy of that distribution. Without immobilization, at 3 weeks, the entropy is large. 6 weeks, the entropy is large. 14 weeks, it comes to this normal band. This is the normal mean plus standard deviation. 14 weeks, the 6 weeks of immobilization, there is nothing for 3 weeks because it is immobilized for 6. You're already in the normal band. And 14 weeks, it remains the same. So this says not immobilizing is not good. Immobilizing for 6 weeks is not required. Immobilizing for 3 weeks, it's already in the normal range. At 6 weeks, it's in the same range as same entropy as for immobilization for 6 weeks. And at 14 weeks, they're all the same. So of the three then, the best is immobilize the joint for 3 weeks. Now some of these perhaps were established by clinical practice. But now we have objective, quantitative analysis to support that practical, experiential observation with quantitative image analysis. Yes, a number of rabbits had to be sacrificed in the study, but that is how clinical research is done. Okay. I skipped some of the details about the Hough radon transform and analysis using edge detection. We did that, but the results were not great. And those formulations are a bit too lengthy. You could read that yourselves later if you wish.
Will that be a part of test then?
Whatever I skipped will not be part of the test. Anything that I skip will not be part of the test. Anything that is too specific to our research project will not be part of the test. But general concepts. From, I say I'm telling a story and you should be able to get some sub-stories and tell them with a few equations as scientists and computer engineers and so on.
Questions for each chapter that you have.
I'm sorry, I didn't get you.
Example questions from each chapter.
Well, if you had the book, you would have those at the end of the chapter. How will you get it?
Quantitative problems also included?
Yes, simple, something you can do by hand. If you were to, did I put them on my website? If you go to Rangayyan.ca and there is the image processing, under my image processing book, I think there is something called tests and exams. All old tests and exams are there, some with solutions. I think I have put it up there. I need to connect to the web to check if it is there. Under my, if you go to the course, not the music, not that, you want the other one. Yeah, but that's within that you go to the engineering one and keep going, and the book, table of contents, biomedical image analysis, and there's some teaching learning material somewhere. Where is that? Maybe I haven't put it up. Teaching files. No. Just a moment, let me search if I have put it here or not. Previously, my website, I had that, but then the university changed the websites. This is my own. I thought I put all the... Yeah. Tests and reports, zip file, image files, zip file. You'll have to download a zip file. So under my image processing book, there is table of contents and updates and corrections, tests and reports, image files that you can download, but these are zip files. I couldn't put multiple files in this. So there is a zip file. If you download that, you will get a whole bunch of previous exams. But those exams are for students taking my course, and those questions may not be relevant here. This is a rapid course. There it is a slow course over 3 months. So some of those questions may be, how should I say, more difficult than what I would ask here. I would give simpler questions here than what you will see there. Okay. So if you go to my website and go to the engineering part, and then under the textbook Biomedical Image Analysis, you will see links to download some of the test images that I have used in the book, and tests and exams, and some seminars also. PDF files of my lectures are there. Okay, let's look at another application with ligament healing again. Dr. Bray, a colleague of Dr. Frank, and Dr. Frank himself were engaged in this project, and this was their project, and we contributed the image analysis part. And Kevin Eng did his research project with me and developed these methods and results. These are microscope images, regular microscope images, light microscope images of ink-stained blood vessels in the rabbit medial collateral ligament. I showed you one of those ink-stained images. The normal ligament is relatively avascular, that is, there are not many blood vessels, and there are a few blood vessels, and they are along the long axis, parallel to the long axis of the ligament. Scar tissue after injury has more abundant network of blood vessels to facilitate healing, and they don't have a preferred orientation, they are not aligned. So this is the process. The picture has come here, similar to what I mentioned earlier. Small differences. This is the knee joint of the rabbit. The ligament is attached there and here, and sutures were put there, and this part was removed. And it was removed after vascular injection of the India ink, as it is called, black ink. And then scar tissue develops, and because the ends are marked by sutures, this scar part is taken out. The original ligament is there in the scar extracted sample. Mid-substance scar is here. And using a microtome, these were sliced to a resolution of, if I remember, at 10 micrometers, thickness of 10 micrometers. So the images look like this. In a normal ligament, this is the long axis of the ligament, there could be a few small blood vessels, and they are parallel to this long axis. After injury in the scar tissue, this is 17-week scar, blood vessels go in different directions. Now this is a destructive way of imaging a 3D sample by cutting it into thin slices and then observing, like a slide, pathology slide, biopsy sample slide, observing under a microscope and taking a picture. Now you may say, well, do 3D CT imaging, but the resolution required here is of the order of 1 or 2 micrometers. Blood vessels are just a few micrometers thick. That is a bit difficult to get even with microcomputer tomography. And the samples are very small. So that was the technology then, anyway, in the 1980s. So the binarization was a problem. With images like this, binarization is a bit difficult because there are very few pixels corresponding to the blood vessels compared to the background. Earlier I talked about bimodal, multimodal histograms or unimodal. These histograms are unimodal because there are so many pixels of the background, very few pixels of the object. So Kevin Eng, who did this project, had difficulty in finding an optimal threshold. So the derivatives were obtained in the horizontal and vertical directions, and the maximum of the 2 derivatives were taken, and then they were summed, and there was another sum computed as the derivative weighted with the original image, and there is a threshold known as the Rutherford-Appleton threshold, which is the ratio of the two. Otsu's method I skipped, but you can go through the derivation of Otsu's method later on. There is a method known as maximal histogram concavity. I mentioned there could be two peaks, like Gaussian superimposed, and in between there is a valley. Find that point of minimum value in the valley, which is concavity between the two peaks. So that is maximal histogram concavity. You can also find peaks by identifying the convex hull of the histogram. And histogram concavity at any gray level is defined as the vertical distance between the convex hull H bar and the actual histogram H. So there are so many of these methods. I'll show the method here graphically. This is one of the original images. There is a lot of noise. The background is not white, but there is a lot of noise in the background. We want these black pixels, which are the blood vessels. After binarization, we get this with a few little other pieces, but those are not false. There is something there. Now we should note that in the ligament, the blood vessels go in all directions. And if you slice them, blood vessels would have gone through multiple slices. And when you cut them, you get just a cross-section of the blood vessel in a given slice. So you will get some artifacts like this. And blood vessels may not go vertically across the slices, but they will weave in and out. They'll be going in and out like that. And when you cut a blood vessel that is curving like that, you will get a small section of that, perhaps like this. So there are artifacts in this process. True 3D reconstruction would be the best, but it's not feasible at this resolution and with this sample size at this time. Now there is microcomputer tomography possible by using synchrotron radiation. In Canada, we have what is called the Canadian Light Source in Saskatoon, not far from Calgary, maybe 700-800 kilometers. It's a huge facility, huge building with an accelerator, not linear but circular, synchrotron. The chamber where the accelerated electrons run is about the size of this room. And there's a big circular donut kind of a building with the chamber approximately of this size. So it's a huge facility, and there's only one in Canada. And at certain points along that electron beam, you get certain types of radiation emitted. And you can get X-rays at a certain specific frequency. And then you can perform tomography, but unlike the CT scanner where the X-ray tube rotates, here the X-ray tube is that huge building. It cannot rotate, so your sample has to rotate. The beam is fixed. Your sample has to rotate and translate. So if you have small samples, you could use that and get resolution of the order of a few micrometers, but you have to make many measurements. Or you can also scan parts of a big animal like a horse that you cannot put in a CT scanner, where the horse has to stay fixed, or somehow you put it on a table that rotates. Yeah, the horse has to be rotated. The beam is fixed. So some arrangement has to be made to obtain the radon transform at multiple angles. There, it is possible to image small samples as well as huge or large samples. But we didn't have access to such facilities then. So how do we get this? The histogram looks like this on log. Log of the histogram. There is a peak here. This is the dark side. The blood vessels are here. This is the background. So the background is much larger than the blood vessels. And the convex hull of the histogram is that. The convex hull is the smallest convex object that completely includes the given object. And it is convex in the sense if you connect any 2 points inside the convex hull, that line must be inside or within the convex hull. So that is the convex hull, and you find the By the way, the Rutherford Appleton gave this threshold. That is not good. Concavity gave this. There is another minimum. The minimum, what was that? It's somewhere there earlier. Anyway, that's another threshold. So we finally took the average of these two, which is somewhere in that. There is noise here. We could have smoothened the image, but so even on a log scale, the two peaks are appearing comparable, but the number of pixels in the background is that much. Then we wanted to perform skeletonization to get the angle at every pixel. So if you take this image, it's a bit hard to find the angle. So if you can just find the skeleton, then at each point we can find the orientation by getting the tangent. The diameter at each skeleton point was obtained by taking the minimum of the distance between the set of contour pixels and the pixel SI. So we saw the skeletonization earlier, so I don't need to go through that. This is the skeleton for the other image I showed earlier, or one of the images. For directional analysis, for every pixel, you fit a straight line using a small window, like a moving window. You fit a straight line, and the straight line approximation is given by this best fitting straight line, sum of xi, sum of yi minus sum of xi yi, normalized by this mean squared value, the square of the mean value and mean squared value here. But we turned it around. If the slope becomes very large, then that fitting method fails. So we took the inverse of that. 1 over m is given by this quantity, and this worked better. So you are just getting the slope, but the inverse of that. At each pixel on the skeleton, we drew the perpendicular and found the distance of shortest pixels of shorter distance on the edges, and got the diameter or thickness of the blood vessels and the area at a given angle, area of the blood vessels for a given angle. And W theta is 1 over cos theta or 1 over sin theta, depending upon angle being less than or greater than 45 degrees. So these are some of the distributions we obtained. Now we have rotated it to go minus 90 to plus 90 degrees, because this is the long axis of the ligament. So this is for normal ligament averaged over 82 images from 4 ligaments, that is 4 rabbits. And this is 17-week scar tissue from 3 ligaments, 115 images. So scar tissue has a broader distribution. Here the binning is finer. We were able to get the angle finer. The filtering angle bandwidth was bigger at 15 degrees. Here we got, I don't remember, I don't want to count how many bins. It's somewhere. So we have finer, maybe 3-degree bins or something, or 6-degree bins. So this is the Rose diagram for a normal ligament, blood vessels now. This is for 17-week scar. So we characterize that using measures of dispersion or variance, entropy. They give similar values, variance and entropy, from different perspectives, but the curves showed similar behavior. So some statistical analysis was done, and a number of images were obtained from a number of ligaments. The entropy values were computed, and standard deviation of those, and percent vascularity, that is area covered in the image. And then a number of assertions were made with certain confidence levels that were computed. The V is vascularization. Vascularization in normal is less than that in the contralateral. The contralateral, that is if the right knee ligament was injured, then the left knee ligament was also analyzed, And there is a contralateral effect. If one side is injured, there is an effect on the other side, possibly because the rabbit is putting more load on the other side. So there is an effect on the other side with a confidence of 70%. Normal, less than mid-substance scar, high, 96% confidence. So he chose to do statistical analysis in this manner, and so on. Compared to the epiligament, that is the layer outside the central core ligament, normal is less than volume of vascularization, less than contralateral is 99%, less than original ligament and 70%, and H is entropy. Entropy of normal less than mid-substance scar, 99%. So very clear. And there are a few others. Essentially, as I said at the outset, in the core of the ligament, there are not many blood vessels in the normal case. And of the few blood vessels, or the few blood vessels that do exist, run neatly, parallelly aligned with the length of the ligament. In response to injury, more blood vessels are formed, and they don't have that parallel structure. So volume of vascularization increases, the entropy of the orientation distribution increases. And then as the ligament heals, it goes back towards normal, but may not reach exactly the normal parameters. Okay? Detection of breast tumors. This was the PhD project of Narasimhadhan. At that time, this was 99, I think, 98 or 99. At that time, detection of masses in mammograms was a big research topic with many, many researchers around the world working on that. The typical sensitivity of detection was of the order of 80-85%, with 2, 3, 4 false positives per image or more actually at that time. The aim was to get it to about 90-95% with 1 or 2, maybe less than 1 false positive per image on the average. That was reached much later, some 20 years later. Perhaps now it is in that range. As engineers and scientists, we quote these factors. What is the sensitivity of detection? That is the percentage of the tumors that you detected. And how many false positives did you mark per image on the average to achieve that sensitivity? If I say every mammogram has a tumor, I'll get 100% sensitivity. But a large number of false positives. That doesn't help. And if I'm too restrictive or conservative in detecting tumors, I can reduce my false positive rate, but I'll miss tumors. My sensitivity goes down. So there is always that compromise. In practice, a radiologist may tend to be cautious in the sense, if there is suspicion, the radiologist may say, let's get more tests done before sending for a biopsy, because biopsy is painful and could cause some other problems, infection and pain. So there will be additional tests like ultrasonography, maybe MR, whatever is available. But if a tumor is missed, then the cancer continues to grow and the patient suffers. And the treatment that is required later when the cancer has metastasized would be more radical or cause more serious problems. So there is always this trade-off. Which side you want to be on depends on the clinic and the preferences of the radiologist, and whether it is a screening program, diagnostic program, who pays for the costs, and so on. In Canada, we don't pay anything. We pay taxes. The money is taken, as I said, before it comes to my pocket. The government has 40% of the money. We get health care, but we have to wait. So there is that. The government controls it. And there's a long wait to get into an MR machine, maybe 6 months, maybe a year. If it is an emergency, things happen right away. If I'm dying, they say, okay, don't die, we'll fix you. But if I simply say I have a pain here, they'll say, okay, we'll take care of you maybe next year, slowly, keep observing. Depends on that. But I can go to a clinic and say I have a pain here, and they will put me in an MR scanner here right away and charge me, I don't know how much. My numbers are still in terms of 1980 when I used to get, 1976, I used to get 400 rupees a month in scholarship for my PhD. I don't know how much it is now, 10,000, 20,000 or something.
Yes.
40,000. After PhD, I got a job, temporary job of as a research associate, project assistant for 700 rupees a month, and I was happy. Now you want at least 1 lakh, maybe 2 lakhs a month. Okay, those numbers are different. I don't know how much an MR scan costs here now, but that's the question of sensitivity versus false positive. In Canada, the tests are free, but I have to go there and get the test done. Here, the tests will cost you money. Every test will cost you money. So you have to pay if there is something suspicious. So when the radiologist says, well, I think there is something suspicious, go and get this test done, you have to pay. The radiologist may say, well, let's wait. But then who knows? There may be the cancer, and it could get worse. So that is the issue in sensitivity versus false positive, or specificity. When one doesn't have the disease, it must be correctly diagnosed. Otherwise, asking for more tests means, again, more cost and needless pain of going through all those tests. So in this method, we develop first wavelet decomposition and low-pass filtering, and then find iso-intensity contours via adaptive density thresholding, hierarchical grouping of iso-intensity contours, segmentation of regions and upsampling their boundaries because we have downsampled to the full resolution image, analysis of the segmented images to reject false positives, and classifications of the regions detected. I mentioned one other thing. At the initial stage, you want high sensitivity even if you allow many false positives. Detect everything that looks like that could possibly be a tumor. But later on, reject all the false positives, or as many false positives as possible. Reject them by applying other criteria. If you miss the tumor at the first stage, that is, if your sensitivity is low, you will not detect it again in the subsequent stages, because the subsequent stages after this are for rejection, not for detection again. So that's an important consideration. The initial step will give us many false positives, and that is fine. The general idea is a mass is denser than the background, breast or wherever, whichever part of the image. A mass means it is denser. A tumor will be denser. And tumor is also active in the sense it is growing and it is spreading. So if you smoothen the image, apply a low-pass filter, all the minor details will be suppressed, and this mass will become like a mountain. And if you were to cut the result into slices based on density, you get iso-intensity contours that are closed loops, where along each contour you have the same pixel value. Like contour maps in elevation. When you have a mountain, you have a flat region and there is a mountain, and the elevation map will show you these contours where the elevation is the same, like maybe here, starting from the ocean, it is 0 and 10 meters and 20 meters and 30 meters and 100 meters and so on. So when you go to the top, there will be a small circle indicating the peak of that mountain. So when there is a mountain or a hill, then there are a number of these iso elevation contours, one inside another, going to the peak. That is the basic idea here too in the detection of masses. But first you have to smoothen the image, filter, low-pass filter, and downsample and create these maps so that minor details like other ligaments, ducts, calcifications, they're all wiped out. You cannot do iso-intensity directly on the original image. It'll be too noisy. So there is a framework for pyramidal decomposition that Naga created. I call him Naga. Mudigonda is what is shown there. That's what I already said. So there is recursive wavelet decomposition and Gaussian smoothing operation, and because you're smoothing, you're getting smoother and smoother images, and it is multi-resolution, and each image is smaller and smaller than the original. Like you may start with a 1024 by 1024, or a 4000 by 4000 image. Next will be 2000 by 2000, 1000 by 1000, 500 by 500, or whatever the step size is. So you get a pyramid of these multi-resolution, wavelet filtered, smooth images. So it is iterative decimation compared to the full resolution image. So there is a hierarchy of sub-images with progressively decreasing bandwidth and increasing scale. So in each of these, you detect these contours, iso-intensity contours, and map them. So wavelet decomposition divides the frequency spectrum of the original image into its low-pass subband equivalent image, FL, and high-pass equivalent detail image. This is standard wavelet decomposition. And the low-pass subband image at each scale is further smoothed by a 3x3 Gaussian kernel, and the result imaging is stretched to the range of 0 to 60 in pixel value, some limited range. Okay, this shows the wavelet in 1D. This is the simlet at 2 scales. The wavelet looks like that, and this is order 8, order 4, order 8. So here is a part of a mammogram. I show only parts of mammograms. We will show the detection in a full mammogram later. So this is the original mammogram, a small part. The width is 51 millimeters. 1024 by 1024. Sub-image. The full image is 4K by 4K approximately. So these are low-resolution filtered images obtained by wavelet filtering. First level of decomposition, this is 512 by 512 pixels and 100 micrometers per pixel. This is after 2 levels, 256 square, 200 micrometers per pixel. And this is third level of decomposition, 128 pixel square, 400 micrometers per pixel. So with the smoothing and downsampling, and the images are displayed to the same size for the sake of display. Otherwise, a pyramid is shown by getting smaller and smaller images. They are downsampled. But you can display to the same size for convenience here. So these are the masses, the 2 bright regions there. So some of these other details are suppressed and the masses get enhanced in this process. Minor details are suppressed. So now segmentation based on density slicing. The assumption here is that recursive smoothing and decimation operations, as I showed in this picture, result in gradual modulation of intensity information about the local intensity maxima in various isolated regions. So intensity levels are expected to assume either unimodal or bimodal histogram distributions. Minor details are removed and gathered, and the histogram becomes simpler. Now you threshold the image at varying levels of intensity, that is, you cut at multiple levels and get the iso-intensity contours. Let me go to this illustration. So here is sort of a peak in the gray level image. That could be a mass. When you cut at these multiple levels, you get these iso-intensity contours, mutually enclosing, or we can call it concentric. They're not exactly concentric, but one inside another. And that could be called a family, because one is inside another. You would call that a family. There could be other such families, but if a family has only 1 or 2, then you say that's not significant. If there is a significant peak, it must contain a number of such contours, one inside another. Then it is a significant peak. That could be a mass or a tumor. There is some modeling here as to what the threshold should be. I'll skip some of these details. So grouping of iso-intensity contours. In the low resolution image, or from the low resolution image, you go to the contour domain. And you get these multiple families of contours at different resolutions, and you want to put them together and get segmented regions. I'll show these pictures now. As you asked, when I skip something, you don't have to read that for the test. I say some of those with reference to the image. It's easier than reading all of that. But you may read all of those if you wish later. But the pictures tell the story. So here is a part of a mammogram that I showed with the two dense regions. There is a third dense region here. So these are the contours, the red lines. The blue lines are the reference, are the contours detected as representations of some dense objects. So if you look at this, there are, I don't know how many, maybe 3 or 4 contours there, one inside another. It is not a significant object. If you were to take this contour, there are more contours inside that blue contour. So the blue contour here is detected as a significant family, the outermost contour of a family of contours within which there are a certain number of contours. I don't remember, 5 or 6 or some number. And that also passed the test. So I can zoom this. So you have 1, 2, 3, 4. Maybe we'll put a limit of 4. You could change that. So this passed the test. The fifth, 1, 2, 3, fourth one, that is the contour. The others are going away. They are breaking, you see there. So the other contours are not enclosing it completely. You see here, there are multiple, 1, 2, 3, 4, and 5, and 6, and 7. That is the 7th one. So in this manner, you detect the outermost contour of a family containing a certain minimum number of pre-specified minimum number of contours. Then it is a family. This is not a family. 1, 2, 3 is not a family. These are rejected. This is something that is not meeting those criteria. So this is the result. This also passed the test. The black contours are the contours drawn by the radiologist independently. So we have 2 false positives. Yeah, the black contours drawn by the radiologist. That's a histogram, let's not worry about that. This is a malignant tumor. I'm showing only that part. And you see so many contours inside the blue contour. I'm only showing that part. So in the case of a tumor, it works well. And that was the black line is the contour drawn by the radiologist, and the white line is the contour obtained by our method. That spicule was missed, so you don't get everything. So benign versus malignant pattern classification was carried out using texture features using Haralick's methods. At that time, we only had 29 masses, 19 benign and 10 malignant, and got an average classification ratio of 0.8. Entropy, second moment, second difference moment, and correlation, those were the shortlisted features from the 14 Haralick's methods, Haralick features. Using adaptive ribbons like I showed around the boundary of the tumor, not the whole region. Now, to detect masses in full mammograms, we need to do a little more. What I showed was how it works on segments containing masses. First, we do detection of breast boundary. You have seen that. So that's the image. Now, this tumor is fairly large. Anyone can see it. But I'll show other examples. The breast boundary, and these are iso-intensity contours. Now, around this mass or tumor, it looks like a thick line, but there are multiple contours there. So if you zoom in, there are multiple contours. It's not a thick line. I'll remove some of this. I want to go to, we did using texture flow field. This was something that Naga added to reject false positives. We found that most of the false positives were caused by overlapping fibroglandular tissue or fibroglandular tissue of high density. Masses were detected, but we were getting these other false positives, like these. But look at the original image, and those are fibroglandular tissue, and here they are intersecting or overlapping. When they overlap or intersect, we have regions of high density. So those were getting detected and passing some of these criteria. You don't have the family of contours for all of these, but some of them still passed. But in analyzing these false positives with the radiologists, we found most of these were strongly oriented fibroglandular tissues. And we wanted to distinguish between the masses and tumors that are true regions of interest and the false detections due to fibroglandular tissues. Rao and Shunk proposed to characterize flow-like information using what they call intrinsic orientation angle and coherence. The orientation is computed at every pixel using gradients, but a 2D Gaussian smoothing filter is applied. We have seen Gaussian filters of that kind. So the impulse response of the gradient of Gaussian filter, you take the gradient and include angle, gradient of that, and that is the gradient of Gaussian filter. So there is a gradient computed with smoothing and orientation. So at each point in the image, the filter HXY, when you convolve, it yields maximal response in the orientation theta that is perpendicular to the orientation of the underlying texture or angle of anisotropy. So what we need is this angle of anisotropy. And how do you characterize that? You get the gradient magnitude and you get the gradient angle, as you have seen before, but now we are using Gaussian, gradient of Gaussian, so to include some smoothing for noise control. Theta mn is just the tan inverse of the y over x. We have seen all of that. So the projection of this vector, gmn, with its angle theta mn to some other angle theta pq is this. So you want to ask, how does it project to other angles? So there is some dominant angle, GPQ, and there is a neighborhood pixel MN. It has GMN. What is that projected to this vector? Which is that. So you want to ask what is common between that and this in terms of orientation and strength. That is texture flow analysis. So the sum of squares of the projections, S equal to sum of G square Mn cos square theta Mn minus theta capital theta, that is the reference orientation. So you do this for all the pixels in a certain neighborhood as shown in that block, 7 by 5 by 5. take the derivative of that and set it to 0 and solve, go through this process. And the estimated orientation angle of flow at that point is this quantity. The gradient vector is perpendicular to the direction of flow. So this is texture flow analysis. Now note that there is another method called optical flow where you are dealing with functions of time. So here it is, nothing is flowing, it's a static image, but how does texture at a point compare to a reference point in terms of gradient orientation, or orientation flow you can call it. Some parameters, let's not worry about that. Now, what is coherence? Coherence is comparing the gradient at 1 pixel with its neighbors. GPQ is the point PQ, the gradient. GMN, the gradient at the neighboring pixels in the 5 neighborhood as shown earlier. Theta Mn is the angle at that location. Minus psi PQ is the angle at this point. So this is the projection, this is the normalization. So this is a measure of coherence. If all of these are in the same direction, that cos theta minus psi will be 0. So you will get a high projection. If there are other angles, the projection will be reduced. So they don't agree in orientation. And if the gradient magnitude is high, and here is also high, you get a large value. So if the gradient is high and the angles agree, then you get a large value averaged over a 5 neighborhood. This is coherence. Ligaments or structures like this, in this orientation will be highly coherent. They have the same orientation and similar gradient, angle and magnitude. So along that axis of the ligament, you will get a large value. Most of our false positives were caused by these ligaments. So we wanted to identify structures that are coherent and get rid of them. Tumors and masses go all the way around. There is no coherence in them. There is no preferred orientation. So these are the false positives. And these are the lines showing the intrinsic angle, the white lines. So if you were to, this was done for the whole image. So if you see around the tumor, the angles go all the way around the edge of the tumor. Here the angles are going in various directions. But if you come to ligaments, these are the false positives that were bothering us. You see the orientation is similar along, not this one maybe, well there is some there. Look at something longer, the angles are the same. So when you analyze those regions, we can recognize them as coherent structures, and even if their density is high, even if we got a high response from the previous method, which is why these were marked initially, false positives, but we will reject them at this stage. There is one here which is inside the pectoral muscle, and we were told that could possibly be a lymph node affected by cancer, which is this tumor. And look at the orientation along the pectoral muscle. These lines go that way, the orientation of the gradient. And look also, in general, the tissues in the breast converge towards the nipple. There is an orientation pattern, there is an overall convergence. That is the oriented pattern that is present in the breast. The ducts, the ligaments, the milk ducts converge towards the nipple, of course, but all the supporting structures also converge that way. And that is shown by this intrinsic angle map. And when there is a tumor, that is disturbed. So that is another method that could help in the detection of tumors. If there is such disturbance in the overall converging pattern of the breast tissues towards the nipple, then there is a local disturbance. We have used that to detect architectural distortion. You will see that later. I'll go a little more. We are almost done. We'll finish this and then stop. This is the intrinsic coherence image where you see large coherence along the ligaments. Around the boundary we get a little bit, but not inside. You have to scale this and zoom it, you will see that. We then computed the features in adaptive ribbons. We have already seen that. The width of the ribbon was defined in proportion to the area of the region and area of a circle containing the region weighted by RC, the radius of the bounding circle. The ribbon size was about 8 millimeters or 40 pixels. So these are the ribbons to compute texture and other features, including false positives. Contrast, coherence, ratio, these are the features computed. Entropy of orientation estimates of the spicules of the margins. Variance of coherence weighted angle estimates. These are all measures of variance alpha I minus mu h, where alpha are the normalized values of the histogram and mu h are the average value of those. So benign versus malignant classification is what we were interested in. So we got some results. Let me just go to the results here. So in this particular case, the tumor was the only one left at the end. All these other false positives were rejected using the additional features I mentioned. This is, Dr. Desertel said this could possibly be a lymph node affected by cancer, but we were not sure of that. So we can say one false positive. This is another mammogram where there is a very small mass. The radius is 5 millimeters. And the initial stage was this. It was detected with so many false positives. And after pattern classification and rejection of false positives, we got that with one false positive. Benign versus malignant classification, the overall accuracy was 0.79, which is not very high. The database was small. So I won't claim anything big about that, but at that time that was substantial. So that paper was published in the Transactions on Medical Imaging. We only had 32 cases, so that's not a very reliable result, but it was an important method and result at that time. So what I would like you to note here is that masses and tumors may be detected by smoothing the image such that they appear as mountains or hills or some large objects with substantial height compared to the background. And then if you do slicing, density slicing, you get these families of contours which will help in separating substantial objects versus insubstantial objects. Still, there will be false positives. You have to analyze what is the nature of the false positives in your application. And in fact, as I said, first, you must allow for false positives in order to have high sensitivity at the initial stage. And then reject. You saw there were so many false positives and most of them were rejected, at least in the two examples. Our sensitivity was, it's somewhere there. We got about 82% or so sensitivity with 2 point some false positives per image, which was reasonable at that time. So analyze the nature of the false positives. In this case, they were oriented fibroglandular tissues. And because they were oriented, we computed the measure of coherence, which characterizes patterns with a preferred orientation, and the coherence is computed with reference to that orientation. Then we could reject those. And the masses, being incoherent with reference to that measure, remained, and they were not rejected. These numbers are not important right now. We are talking about the methodology. Okay, we have crossed 12:30. Do you have any questions before we break for lunch?
I want to see the first example. In the slides. I want to see the first example in the slide. The mammogram.
The one with the big mass?
Yeah. This one. So isn't it near the pectoral muscle?
It is near, the pectoral muscle is here. This is inside the pectoral muscle. The tumor is in the breast portion. There is a little bit of separation, yeah.
The radiologist said that it would be a problem in the lymph node. So what is the classification that he said then? Why can't it be a tumor as well?
Which one? This one?
Yeah.
That's not the breast. That's the pectoral muscle behind the breast. So it could be, it is typically a lymph node that could appear there, and if that is affected, it'll show up as higher density. So it wouldn't be called a tumor, it is a side effect of the tumor. And it is not in the breast, technically speaking or anatomically speaking there. So the breast tumor is this one. The other is some other dense region in a, you can say, different part of the body, but it is just a muscle near the breast. But it's the pectoral muscle. It could be a secondary tumor if you want to call it so. But I was told by Dr. Desatel that it could be a lymph node that's been affected and is showing up with higher density in the pectoral muscle. That is what the radiologist told us. So it's a difference in terminology. In the lung, perhaps you would say, if there is another region like that, you would say it is a secondary tumor. So here it's not called a tumor. And we didn't want to call it a false positive because it has some relevance in diagnosis. But if you just look at detection of tumor, that is a false positive.
Thank you.
Okay?